This video introduces Stirling's approximation, which is both an amazing formula and useful. So let's nail some notation. If you have two real-valued sequences, and the limit as n goes to infinity of the ratio an over bn, so an is a real-valued sequence, bn is a real-valued sequence. If this limit is equal to 1, then what we write is an is asymptotic to bn, and we denote that with this squiggly line. So an is asymptotic to bn. So for some quick examples, n to the fifth plus 2n plus 1 is asymptotic to n to the fifth. Because if you divide these two and take a limit as n goes to infinity, you get 1. Only the leading terms really affect the behavior for large values of n. So this is why the end of the fifth term is important in both of these sequences. Similarly, I could have like 2 to the n plus n 3 to the n plus n squared. That's asymptotic to n 3 to the n. This is the term that dominates the behavior for large values of n in both of these sequences. Here are some basic facts about this relation. So facts. This is an equivalence relation. On the set of real-valued sequences, say. So it's reflexive, transitive, and symmetric. Another fact is if an is asymptotic to bn and cn is asymptotic to dn, then it follows that cn is asymptotic to bn dn. So these facts you can prove with basic properties of limits. They're really not that difficult to show. I will point out, though, that if you replace the multiplication in this statement with addition, then the statement is no longer true. Okay, so what is Stirling's approximation? It's this amazing theorem. Gamma of n plus 1 is asymptotic to the square root of 2 pi n times n over e to the nth power. So it's really quite shocking that the gamma function can be asymptotic to something involving the square root of 2 pi. I have an e in here. It's just beautiful. So I'm going to show you why this is true. So here's a proof. I'm going to define a function f of n in the following way. So it's going to be equal to 1 plus x over the square root of n to the n power, e to the negative square root of n x, if x happens to be bigger than or equal to, or let's say bigger than, the square root of negative n, and I want it to be 0 otherwise. So I have this strange looking function, and understanding properties of this function will allow me to prove Stirling's approximation. Well, then I could take the log of this function, so the natural log of this function, and I can use basic properties of logarithms, meaning that log of a product splits into a sum. I can factor exponents down. So using basic properties of logarithms, I get this is equal to n log 1 plus x over the square root of n minus square root of n x. Of course, that's if x satisfies this property. So let me just write if x is bigger than negative root n. Now, I can simplify this a little bit. I think we've seen in our past the series expansion of a function of the form log 1 over 1 minus t. That's the sum and going from 1 to infinity of t to the n over n. And I could adapt that for this situation, so I can rewrite this logarithm to make it look exactly like what you see here. And I can simplify and then look at the series expression. So if I expand everything as a series, it turns out that the first non-zero term in the series expansion of this will cancel with the minus nx here. And when you expand as a series, you'll find negative x squared over 2 plus x to the third over 3 times root n minus x to the fourth over 4 n squared. The next term I think would be x to the fifth over 5 n to the 3 halves, and this goes on and on. The key observation that I'm trying to make is that every term past the first involves a division by some positive power of n. So what this means is, therefore, the limit as n goes to infinity of log fn of x is simply minus x squared over 2. By the way, as n goes to infinity, this condition enlarges to encompass the entire real line. So I have this is true for all x, and thus the limit as n goes to infinity of fnx is e to the negative x squared over 2. Okay, so I've defined this crazy function. I've found that the limit of that function as n goes to infinity is e to the negative x squared over 2. Now I will prove the final result. Thus, the square root of 2 pi is well known to be the integral from negative infinity to infinity of e to the negative x squared over 2 dx. I'm not proving this in the current video, but you can prove this result by squaring both sides, writing the double integral in Cartesian, and translating that into a double integral in polar coordinates. Then when you integrate in polar coordinates, you could find the desired result. So this is a well-known Gaussian integral. It's not too hard to prove using the technique that I showed that this identity holds. Now I'm going to use this fact we have about the function fn and write this as the limit as n goes to infinity of the integral from negative infinity to infinity of fn x dx. Now, I did something slightly sneaky there. I interchanged the operation of the limit and the integral. The integral also is a limiting operation, so you need to be a little bit careful when you switch the limit and the integral. However, we're safe here using the dominated convergence theorem, so I'm not going to prove it, but this is actually a step that you could justify using the dominated convergence theorem. So now I will evaluate this integral, so f of n is this function. I'd like to do a u substitution, or maybe I'll do a t substitution. So I'm going to do a substitution. I'm going to say t is equal to x times root n minus n. Oh, excuse me, let me do plus n. And then dt is square root of n dx. If you evaluate this integral by doing the substitution, then you will find the limit as n goes to infinity. Now I'm going to integrate. So if x is this quantity, because f of n is 0 if x is not satisfying this condition, when I change into t, the integral grows from negative infinity to infinity into 0 to infinity. Then if I do the substitution, I get an extra 1 over root n from this dt equals square root of n dx fact. I'm going to do this substitution for t in the definition of the function fn, and I will find 1 plus t minus n over root n, oh, excuse me, just n, to the n power, e to the n minus t dt. Okay, we are almost there because this is equal to, so this line that I'm saying is equal to, I'm going to write the limit as n goes to infinity. I'm going to factor out a 1 over square root of n. I'm going to factor out an e to the n power. And I'm going to factor out an n to the n. So if you combine these two terms, you could factor out an n to the n. And what I'm left with is the integral from 0 to infinity of t to the n power e to the negative t dt. Look at what we have. This is wonderful. This is wonderful. So this is actually equal to the limit as n goes to infinity. This is my gamma function. This is gamma of n plus 1. So I'm going to put that on top here, gamma n plus 1. And on the bottom, I'm going to put square root of n divided by e to the n power. And I think that completes the proof of the statement because I could just divide both sides of this equality by the square root of 2 pi, and I get Stirling's approximation. An amazing result. So we'll use this in future videos to find asymptotic formulas for coefficients in generating functions. Please follow me along there.